I'm Dr. James Wotton from the University of Basel, and I'm here with Dr. Michael Kastoryano from the University of Copenhagen, is it called?
That's right, Niels Bohr Institute.
Yep, so he has developed, along with some other people, a great algorithm for quantum error correction, and he's going to tell us about it today.
Yeah, thanks. So the algorithm was developed with Michael Harold, Earl Campbell, and Jens Eisert. So to translate the idea of the algorithm into more familiar terms, what we can call this is something like the game of life in ancient Greece. So what we're going to do is going to be vaguely reminiscent of an old thought game by Plato in his famous Symposium, which is the following: that Zeus created humans, or living entities, or soulful entities, in pairs. And then to punish them, if they'd been naughty, well, I don't exactly know why they punished them, but the idea is when they were sent onto Earth, it was a punishment. And the punishment was that you lost your pair, or your soulmate, as it was called. Now, in Plato's version, there were three different types of soulmates. There could be men-men, women-women, or men-women. In our game, we're going to have only one type of individual, so no sex associated to it, but these individuals do have soulmates when they're brought onto Earth. Now the problem is you don't know exactly who your soulmate is because all the other individuals look absolutely identical. Now you imagine a population of beings that have been sent down to Earth. Now, let's say Earth is just a ballroom or a discotheque. So there's a finite number of other individuals, and one of those other individuals is going to be your soulmate. And your goal in the game is going to be to find your soulmate. So now let's look at a new game where we're cheating a bit, and we actually can see our soulmate. So this isn't how the real game goes, because in the real game you can't see the color of your soulmate. And now every single individual here is going to be simultaneously looking for their soulmate. Some people are faster than others, and that's going to be represented sequentially. So let's imagine the pink ones find each other first, and the blue ones find each other. Now it looks pretty simple when okay, and it's worth saying that when the soulmates are thrown onto Earth, they're thrown down close to each other, not thrown down at very distant parts of the ballroom. So the gray soulmates can easily find each other because they expect that their soulmate is going to be close to them. So I'll put them together. And now you look at these Bordeaux and green soulmates. And if you focus on this individual, it's going to be very hard for him or her or it to decide which one of the other individuals are their soulmates. So let's say they choose the wrong soulmate, they get eliminated. Let's say if you couple yourself with your wrong soulmate, you get eliminated from the game, sent down to hell instead of back up to heaven. But then there are two isolated soulmates that sort of take over the role of the previous one. So now these two Bordeaux ones are soulmates, and you try to bring them together. Another set of individuals have been thrown into the ballroom, and now once again they're going to try to find their soulmates. So the idea of our algorithm is that individuals are not very patient in their choice of mates. So what they're going to do is they're going to go to the region of the ballroom that has the most mates instead of searching for an individual mate. So imagine you're this red individual here, and you look around yourself 360 degrees, and you say, okay, where is the closest mate, and where are the most mates? And somehow these individuals have to figure out a way of finding a compromise between the part of the ballroom that has the most mates versus the closest mates. And typically you're gonna weigh the proximity of your mate as being more important than the number of mates. So the red one is going to choose to go to the left instead of going to the right. Now it can happen that okay, now If you take, for instance, this yellow individual, there are a lot of mates to its right and to its bottom, but they're quite far away. So it's going to decide to go to the mates that are towards its top or left. Now, suppose it's going to choose between its left mate and its top mate. One argument of choice would be, okay, to the left there's only one mate, but to the top, if you look just a little bit farther, there's going to be a second mate. So we're going to choose to go to the top. This is, of course, the wrong decision, but it's a systematic decision that is going to be made. And we'll take this as our basic rule for finding mates from now on. You look at your 4 neighbors. If there is a neighbor that is a mate, you go there. If there is a mate that's one of your nearest neighbors, you go there. If there isn't any, or if there are 2, then you go to the direction where there are more mates. So here we don't have any of these cases. You have to wait until there are more. So an example would be this individual. There's a mate to the north and a mate to the south. So how does he decide whether to go north or south? So what he's going to decide is going to look just a little bit further to the diamond around him or her. And clearly there's going to be a mate in this larger diamond that's going to be northeast. So this individual is going to decide to go for its northern mate. Now similarly, for this individual, the individual has no mates that are directly neighboring it, but it does have one individual that's a distance 2 away. So it'll go in this direction, and so on and so forth. Now you lose the game if mates get dragged to one side of the ballroom and the other. So now let's try a game where you don't actually see who your mate was, but you perform choices according to these rules. Now, an ambiguity in these rules is that you don't know what individuals you decide to move first. So that's a matter of taste. What I'm going to try to simulate is doing this at random, but of course any human activity is not going to be at random. So for the purpose of illustration, I'll start with the hard decisions, because the easy decisions are obvious. So in this case, the individuals are faced with a hard decision of going north or south, and clearly this individual is going to decide to go north. This individual has an equal probability of going left or down, so we just randomly choose left. And now the choices are pretty obvious. Okay, actually not. If I focused on this individual, I would be inclined to go southwards, although in retrospect we know that this is probably a bad choice. So let's say this individual goes down. Now we start again. By parity, you notice that when you have small clusters of 3 individuals, probably something went wrong, because probably one of the individuals has a soulmate that's a bit farther away. So maybe these are the cases that we want to take care of first, because the more distant cases, the more obvious cases like this one, don't have any ambiguity in them. So let's focus on this individual that could go right or south. It seems that there are more neighbors to the south than there are to the right. We'll go down. And in our game, having isolated individuals is very dangerous, because you lose as soon as 2 soulmates become isolated from their respective soulmates and drag from one side of the ballroom to the other. So we'll try to bring this guy down to some other cluster. Okay, now we've got another set of individuals coming into the lattice. And now if you think about what's happening on a more macroscopic scale, if you zoom out from the specific individuals and you look from a certain distance above the ballroom to see how these individuals act on average, well, you're going to notice that on average they're going to tend to all want to cluster into groups. They don't like to be isolated. And so what you're going to do is you're going to try to imitate this activity. So this guy doesn't want to be isolated, wants to follow a group. This guy is going to be distant from, this guy is going to be completely isolated. And so it now has to choose whether it wants to be associated with the group to the left or with the group south of it. Let's randomly decide that it should be associated with the group south of it. So now clearly we have two clusters of individuals, or something that looks like two clusters of individuals, and want to bring these clusters together and keep them as separate clusters. Okay. Now somehow this one cluster completely disappeared, which is probably a random fluctuation. But let's again now try to keep the clusters together. Okay, now since the number of individuals is quite small, clusters tend to disappear. Okay. Here, let's bring the individual guys into clusters, and so on and so forth. Now, at this point, it's very hard to find out whether this was a good strategy or not. It seems as though it is, as the isolated individuals seem to be disappearing at each step. Okay, now let's try to purposely lose. This is also not so easy.
No. Yeah, so this being based on multiples of 2 rather than multiples of 10, we don't know what the high score would be. But if you want to try it out yourself, find it in the link below. Thanks a lot to Michael for explaining his method to us. Of course, we don't usually play a game based on multiples of 2. We usually play it based on multiples of 10. But it's up to you to work out how you might be able to generalize his method to this. But here we can think of this as being 7 ones sitting here. This is 3 ones sitting there. They have been separated from each other by the wrath of Zeus, but we can bring them back together and all is well with the world. And here we've got 9 and 9 and 2, which are all a big lump of 20 that want to be together, so we can bring them together too. And so on and so forth, using the same sort of methodology as we find in Michael's method. So once again, thanks to Michael, and thanks to you for watching.